In this video, I'm going to go through the quarterly review packet, so if you have any specific questions, just go to the description and jump to whatever question you need help with. Number 1. If triangle MNO is congruent to triangle XYZ, then which of the following can be concluded using the fact that corresponding parts of congruent triangles are congruent? Remember, that's just that CPCTC idea. So part of this is recognizing that the order of the letters matter when you're looking at a congruent statement for triangles. So that's saying that angle O should match up with angle Z, and side MN should match up with side XY because those are the two letters that come first, so things like that. So let's go through some of these examples. A. Angle MNO is congruent to angle ZXY. Well, remember, the middle letter represents the vertex of this angle, so this is really saying that angle N should match up with angle X. But if I go to my congruent statement, N is in the middle here, and Y is in the middle there, so really it should be that N matches up with Y, so that doesn't work. For MO, congruent to side XZ, well, let's take a look at that. MO are the first and last letters here, and XZ are the first and last letters there. So those are the sides that should match up. Again, if you go through these for C, this is saying angle NOM, or just angle O, and angle XYZ, or just angle Y, should match up. But I know that angle O should match up with angle Z, so that doesn't work. And you can make a similar argument for why MN shouldn't match up with ZX. It should match up with XY instead. So just look at the order of the letters there. Number 2. If a regular pentagon, remember that's a 5-sided shape, is rotated around its center, which of the following would not be the correct number of degrees such that it will coincide with itself? Well, remember, we could take 360 degrees divided by the number of sides, and that'll tell us the minimum angle of rotation to get the figure to lie on top of itself. So I know that 72 degrees is definitely going to work. And I know if I spin a figure 360 degrees around, I end up exactly back where I started, so that's also going to work, and I'm looking for which one would not be correct. So now we're looking between 36 degrees and 216 degrees. Well, if I keep adding rotations of 72 degrees, I notice that, okay, if I rotate 144 degrees, that'll also have the figure land on top of itself. And if I go another 72 degrees, that will also have the figure land on top of itself. So any multiple of 72 is going to work here. And 216 is just 72 times 3. So 36 degrees is just a little too small to get me to land on top of itself there. Number 3. A sequence of transformations maps rectangle ABCD onto rectangle A double prime, B double prime, C double prime, D double prime, as shown in the diagram below. Which sequence of transformations maps ABCD onto A prime, B prime, C prime, and so on? Right, so I'm going from here, and then from there to there. So I want to start with my first transformation to get from my original to my first image. Well, if I'm trying to visualize this, it looks like I flipped it right over the x-axis, so I know I'm going to start with definitely a reflection. Right, because if I count the distance from D to the x-axis, that's the same as the distance from D prime to the x-axis, and I can do that for any of my points. So really, I just need to figure out what happened from my first image to my second image. And it doesn't look like I reflected it, so as I'm going through my answer choices, none of them have a reflection as the second one, but I know I didn't translate to start, so I could rule out C and D. Remember, translate just means to slide, and because the points wouldn't match up, A would go to D prime if I slid, a translation's not going to work here. And it doesn't look like I translated to get to the other one either, so I know it can't be B, because if I translated, it would look something like that. It would be in the same orientation. So my only option here is that I must have rotated it some number of degrees, probably about the origin, to get C to land up there and B double prime to land up there, and so on. So try to visualize what's happening here step by step. Just visualize the first step. Notice I didn't even look at the answer choices there. And then try to visualize the second step. Number 4. Which point in the graph below is the image of point P after a counterclockwise rotation of 90 degrees about the origin? So let's hone in on point P there. Remember that counterclockwise is the opposite of the direction of a clock, so I'm moving this direction around my origin. So if I'm going 90 degrees, I should probably end up somewhere about here. B would be just a little bit too small. That doesn't look like a 90-degree angle there. But if I'm looking at point A, notice that if I connect the origin to P and connect the origin to A, that looks like that could very well be a 90-degree push in the counterclockwise direction. So I would say that point A would best represent the image, counterclockwise rotation of 90 degrees if I go around the origin. Number 5. Which figure always has exactly 4 lines of reflection that map the figure onto itself? Well, remember a line of reflection, so I'm going to actually start with a regular triangle or an equilateral triangle that has 3 equal sides. A line of reflection is just a line that if you reflect the figure over it, it lands exactly on top of itself. So if I'm looking at a triangle here, I could draw a line of reflection through any of these vertices, and if I flip the triangle over that line right there, it would land right on top of itself, or that line right there, and so on and so forth. So you're really just looking for symmetry here. So an equilateral triangle is going to have 3 lines of symmetry. Let's take a look at an octagon. If you remember, that has 8 sides. And if it's a regular octagon, that means it has 8 equal sides. So just like how an equilateral triangle has 3 lines of symmetry, an octagon will just have 8 lines of symmetry. Let's take a look at a rectangle. A rectangle definitely has 1 going up straight through in that direction, and it has a second one if I fold it across the middle right there. But if I take a look at one of these diagonals, notice that it doesn't line up perfectly. So if I try to look at that as one of my lines of reflection, I'll erase the other 2. If I flip this point over the line of reflection, it would land somewhere right there. And if I take that corner and flip it over the line of reflection, it would land somewhere right there. And the whole idea is that I want my figure to land on top of itself. So this figure isn't going to work out with more than 2. So a rectangle only has 2 lines of reflection. Now remember, a square is just a quadrilateral with 4 equal sides, and you can sketch in the 4 lines of reflection there. We have the 2 from the rectangle that go straight through my opposite sides, but since a square has 4 equal sides, if I take a look at those diagonals there, so something like that one right there, if I flip this corner over the line, it's going to land perfectly on my other corner over there, and you can make a similar argument for your line of reflection going through the other pair of vertices too. So altogether, this is actually a regular quadrilateral. It's got 4 equal sides, so there should be 4 lines of symmetry. Number 6. In the diagram below, the measure of angle BDC, so right over here, is 100 degrees. So I'm going to mark that. The measure of angle A is 50 degrees. And the measure of angle DBC, right up there, is 30 degrees. So I'm going to mark all those. Now, it says which statement is true. And I'm not even going to read these. I'm going to try to fill in whatever angles I have. If I'm looking at triangle BDC right over here, remember that for any triangle, the angles in a triangle should sum to 180 degrees. So I already have 100 degrees in one angle and 30 degrees in another. So if I take 180 and subtract the 130 degrees I already have, I could find out that my missing angle for angle C is 50 degrees. Now let's see what else we can notice. Notice that these 2 angles form a straight line together, so they should be supplementary. Remember, that means they should sum to 180 degrees as well. So if one of my angles is 100, my angle on the other side should be 80 degrees. Now, similarly, if I'm looking at triangle ABD, right now I'm just doing some detective work to figure out what angles I could fill in here. I have 2 angles and I'm just missing 1 angle of a triangle. So again, I can add my 2 angles up, 50 and 80, to get 130 degrees, and I could subtract that from 180 to find that my missing angle ABD up there should be 50 degrees as well. So now let's go through the answer choices and read. Triangle ABD, I'll trace that out, triangle ABD D, so that one on the left side right there is obtuse. Well, remember, an obtuse angle has to be greater than 90 degrees, and I don't see any angles that are greater than 90 degrees there. So that can't be an obtuse triangle. Triangle ABC, so the big triangle altogether, is isosceles. Well, remember that an isosceles triangle has both two congruent sides and two congruent angles. And if I'm looking here, it looks like I've got that base angle of 50 degrees for A and that base angle of 50 degrees for C, so because there are congruent base angles there, triangle ABC must be isosceles. Just to go through the rest of the answer choices, the measure of angle ABD, if I trace that out, ABD, that's 50 degrees, not 80, so that can't be it. And remember that a scalene triangle has three different angles and three different sides. But if I look at triangle ABD, I still have two congruent angles, so that's technically an isosceles triangle as well. So I wouldn't be able to say that that is scalene. All the angles would have to be different in that triangle for that to be a scalene triangle. Number 7. In the diagram below, segment EF intersects segment AB and segment CD at G and H respectively. And GI is drawn such that GH, that segment right there, that segment right there, is congruent to segment IH right there. So I'm going to mark those just with tick marks so I know they're congruent. If the measure of angle EGB right there is 58 degrees, and the measure of angle DIG, that obtuse angle right there is 119 degrees, explain why, that's a typo, be careful. That should just say, explain why AB is parallel to CD. Right, so why this segment up here is parallel to that segment down there. So essentially we want to find either congruent corresponding angles, or we want to find congruent alternate interior angles. And both of those would be enough to explain why my segments here are parallel. So let's see what else we could fill in. The first thing I notice is that these two angles right here should be supplementary because they add up to a straight line. So if I subtract my 119 degrees from 180, I find that that first missing angle should be 61 degrees right there. And if you look at triangle GHI, notice that there are two congruent sides there, making that an isosceles triangle. So if two sides are the same, the angles across from those sides should also be the same. So even though this looks like it's flipped a little bit, if I have that 61 degrees over at I should also be able to put that 61 degrees over at G, because those are my congruent base angles of that isosceles triangle. So there's a lot of information you could choose to fill in at this point. You could try to figure out that angle up there because all three of those angles should sum to 180. But if I'm looking at my triangle right in here, I'm noticing that I have two angles, and if I add 61 and 61, I have 122 degrees. And if I subtract 122 from 180, I find that my missing angle right there is 58 degrees. And again, this is only one way to do it. There's a whole bunch of ways you could do this. Now, I'm actually already finished at this point, because if I'm looking at just my parallel lines cut by this transversal right here, notice that I have shown that I have congruent corresponding angles that I've marked in blue there. Those are both 58 degrees, and congruent corresponding angles form parallel lines. If you didn't want to use a corresponding angle argument, just because you're used to working with alternate interior angles, notice that 58 degrees up there. That's vertical with angle AGH up there, so I could say that's 58 degrees. And if I'm looking for my alternate interior angles or tracing out the Z, notice that at G and H I have 58 degrees. So I can make an argument to say that angle AGH is congruent to angle GHI. And I know that makes the lines parallel because congruent alternate interior angles form parallel lines. So that's the main idea there. You could either look for those congruent corresponding angles that we started with, or if you prefer to get alternate interior angles, you could use that vertical angle trick that I used up there. Number 8. Triangle MNP is the image of triangle JKL after a 120 degrees counterclockwise rotation about point Q. If the measure of angle L is 47 degrees, right there, I'm going to mark that, and the measure of angle M is 57 degrees, determine the measure of angle M. So, a couple things you need to worry about here. The first thing is that we know rotation is a rigid motion, and rigid motions preserve both distance and angle measure, but here I'm only looking at the angle measure. So if I'm trying to visualize this, P, if I rotate, should have matched up with L, so I could also mark angle P as 47 degrees. Now look at this. I've got a triangle with two angles, 47 and 57, and I'm only missing one. So if I add up 47 and 57, I get 104. And again, if I subtract from 180, I can find that my missing angle for M should be 76 degrees. So the two big ideas that we used here were that rigid motions preserve angle measures, so I could mark angle P as 47 degrees, and that the angles in a triangle should sum to 180 degrees. That's how we figured out M by subtracting. So my answer here is angle M is equal to 76 degrees. And if I ask you to explain, you just got to give me something in words to explain your thoughts onto how you got there. For number 9, triangle ABC is shown below with vertices A, 3, negative 2, B, 3, negative 6, and C at 9, negative 2. Draw triangle A prime, B prime, C prime, the image of triangle ABC after 90 degrees counterclockwise rotation about the origin. Right, so if you remember that a 90 degree counterclockwise rotation just means to take your points, swap the coordinates, and negate the first one. So that's just a rule you need to memorize from earlier in the year. Or you could turn your paper and try to recognize that, well, if I'm rotating 90 degrees counterclockwise, I should end somewhere in the first quadrant right there. So that could be a way to help you. So the way I organize my work here is I start by just listing my coordinates that I have, and I'm going to apply that transformation to them. So C is 9, negative 2. So to get A prime, I'm going to swap my coordinates and negate the first. So that's going to become 2, 3. I'm going to swap my coordinates, and that negative 6 is going to bump to the front and become a positive 6. Again, that negative 2 is going to bump to the front, become a positive 2, and the 9 goes in the back. So I'm going to take a second to plot these coordinates just to make sure I applied this correctly. Alright, that looks pretty good to me because the triangles look like they're still congruent, and it looks like I spun at 90 degrees. So remember, rigid motions should preserve distance and angle measure. So if these triangles don't look congruent, try plotting them again. Draw a triangle A double prime, B double prime, C double prime, the image of triangle A prime, B prime, C prime after a reflection in the y-axis. So remember the y-axis, y to the sky, that's the one that goes up and down. The easiest way to do this is just by counting. A prime is 2 units away from the y-axis, so I'm going to go 2 units left to get A double prime. B is 1, 2, 3, 4, 5, 6 units away, so I'm going to go 1, 2, 3, 4, 5, 6 units away. I'm in for C prime, C double prime as well. That's 2 units away right there. And again, so this should look like you flipped it over the y-axis. Now it also says to state the coordinates of my triangle too. So just make sure you give me the coordinate pairs that represents each of those points. And make sure again you're using double prime here because we've already used prime for my first image. For number 10, I took a second to plot these triangles already. It gives me the vertices of triangle ABC, and it gives me the vertices of triangle DEF. It asks me to graph and label the triangles on these axes below, so I took a second to do that. If you didn't, take a second to do that right now. And it says to determine and state a single transformation that would map ABC onto triangle DEF. Well, to me this looks like a reflection, but it's not over the y-axis or the x-axis. It looks like if I'm trying to draw on a line of symmetry, it it would be like right there. So I definitely know this is going to be a reflection, but I need to state what line I'm reflecting it over. And if you remember, for vertical lines, those are always of the form x equals, and all of the x values on that line are -1. Now the way you could figure that out is you could look at 2 points on this line, or really any points, and that every point on that line is going to have an x value of -1. Similarly, you can make an argument for some sort of horizontal line that if you pick any point on that line, all of the y values are going to be the same, so that's going to be a y equals line. That's how you could figure it out if it's not the y-axis or the x-axis. Now it says to use your transformation to explain why triangle ABC is congruent to triangle DEF. Well, I know a reflection's a rigid motion, and rigid motions, like we've talked about before, preserve two things. They preserve distance, or you could say side length, and angle measure. So if they preserve distance and angle measure, it must be the case that none of the sides changed and none of the angles changed. Number 11. As shown on the set of axes below, triangle GHS has those vertices. Graph and state the coordinates of G double prime, H double prime, S double prime, the image of my original triangle after a rotation of 180 degrees, followed by a reflection. So the followed by is going to be the second thing. That's going to be the second thing I do. The first thing I'm going to do is the rotation. So if you think about rotating 180 degrees, I'm probably going to end up somewhere around here. So that's a good place to start. If you don't remember the rule for that, you could either turn your paper 180 degrees, or just remember that your original point should go to -x, -y. So the way I'm going to organize this is I'm going to start by just listing my 3 points. G is 3, 1, H is 5, 3, and S is 1, 4. And I'm going to apply that first transformation. So I'm going to rotate 180 degrees. So my G prime is me just negating both my coordinates. And again, that's a rule that you got to look back at for those bump switching rules that we used earlier in the year. Alright, so that's where I'm going to plot my first triangle. I'm going to take a second to do that. Alright, so I plotted my first transformation. I labeled it as G prime, S prime, H prime. And that's my rotation of 180 degrees. So the thing I still need to do is reflect over the x-axis. So that's pretty easy to do by counting, right? I could just say that, okay, G double prime is going to be up there, 1, 2, 3, H double prime is going to be up there. And if I count S, it's 1, 2, 3, 4 away, 1, 2, 3, 4. So it's going to look something like that. And again, you should use a straight edge to connect these points. For me, I'm not going to here. Okay. So first thing you need to be worried about is that it says to graph and state the coordinates. So I still need to state what my coordinates would be after I reflect over the x-axis. So if I'm counting, I see G double prime here is just -3, 1. H double prime here is -5, 3. And S double prime is just -1, 4. So my final answer, that's part of it, me stating the coordinates, and the other part is me graphing it over there. Number 12. Given the right triangles ABC and DEF, where angle C and angle F are right angles, AC is congruent to DF, CB is congruent to EF, describe a precise sequence of rigid motions that would show triangle ABC congruent to triangle DEF. So really, I'm just looking for a sequence of rigid motions that would map this triangle right here directly onto my other triangle. And if none of my points are connected, the first thing I'm going to do is I'm going to start with the translation. So I'm going to translate point C to map to point F. So I'm going to take my triangle right here, and I'm just going to slide it, let's see if I can do this, until point C lands on point F. So something like that. All right, that's not that bad. Now, you should notice you're almost done here. If I flip over the line created by DF, I'd be done. So my last step is just going to be reflect over DF. So I know that that point, that like B prime over there is going to go right over and land straight on E where I need it to be. So what you need to be worried about is that when you're talking about reflections or translations, make sure you're being specific and using the points that they give you. If you don't know how much to rotate, describe where the point should land up. If you don't have an X or a Y axis, you need to make reference to the segments they give you. So I said reflect over DF, because I knew that was that segment right over there, and I'm trying to visualize me flipping that triangle so it lands on top of DFE. Number 13. Given AE bisects BD, angle A congruent to angle E, prove triangle ABC congruent to triangle EDC. So I always like to mark up my picture just a little bit. They tell me those angles are equal, and they also tell me that AD is bisecting BD. Remember, that means that BD is being split into two congruent segments. So if I start with my givens, if I'm reading my statement here, a segment bisector divides a segment into two congruent segments. AE is the guy who's bisecting BD, so my two congruent segments are going to be BC and CD. Now, the next statement says that angle ACB, so that angle right there, is congruent to angle DCE, that angle right there. Now, anytime I have two intersecting lines, the angles across from those are going to be congruent because vertical angles are congruent. So I'm going to use that as my reason there. Vertical angles are congruent. So notice I've got two angles here. I've got an angle, and the side that's not between those two angles. So the reason those two triangles are congruent is just by angle, side. Number 14. Given segment PR congruent to segment TR, it's already marked in my picture, segment PQ parallel to segment TS, prove triangle PQR congruent to triangle TSR. And my first statement that I need to worry about is it says that angle P is congruent to angle T. Well, think about, if I'm getting told that I have parallel lines, they want me to be looking for alternate interior or corresponding angles. In this case, angle P and T are congruent alternate interior angles. So my reason for that is that parallel lines form congruent alternate interior angles. I could use that anytime I have parallel lines in the givens. My next statement is that angle PRQ is congruent to angle TRS, and again, those are just vertical angles. So my reason is that vertical angles are congruent. And your last step should always be exactly what you're trying to prove. So by angle, side, angle, triangle PQR is congruent to triangle TSR. Number 15. AB congruent to DC, segment AB perpendicular to BC, and segment AD perpendicular to segment DC. Remember, the perpendicular lines form congruent right angles, so I already marked those right angles for you there to help you out. Now, the first statement I need to worry about for this fill-in proof, AC is congruent to AC. That's because they share that side, these two triangles, in common. So I'm going to say that's the reflexive property. Anytime something is congruent to itself, that's reflexive. Now, triangle ABC, that right angle right there, should be congruent to triangle CDA, that right angle right there, because perpendicular lines form congruent right angles. And again, you could use that anytime they give you perpendicular pieces in the givens. That's why they're telling you they're perpendicular. They're saying look for right angles. So I've got an angle, I've got a side, and I've got another side as I'm tracing it around. But remember, angle, side, side is one of those postulates that doesn't work unless it's a right triangle, in which case we call it HL, for hypotenuse leg. Number 16. Segment RT bisects angle SRV. Angle SRV is getting bisected. Angle S congruent to angle V. Prove triangle SRT congruent to triangle VRT. So the first thing I want to look at is this statement right here, that angle SRT, right there, is congruent to triangle VRT right there. And I need to look back to my givens to see why that's true. They're telling me that I have a bisector. And remember that an angle bisector divides an angle into two congruent angles. So just like a segment bisector, I'm just replacing the word segment with angles in that reason. A segment bisector divides an angle into two congruent angles. Again, these two triangles share a side, so I could say that RT is congruent to RT by the reflexive property. So by angle, angle, side, these two must be congruent. Again, the side isn't between those two angles, so I know it's not going to be angle, side, angle. That would be if instead I had these two angles over here, because the side is now in between the angles. Number 17. Segment AB congruent to segment DC, segment AB parallel to segment DC, and segment BC congruent to segment CE. Now, the first statement is asking for what's the statement that goes with that reason. Parallel lines form congruent corresponding angles. Remember that if I've got parallel lines cut by a transversal, corresponding angles are angles so that when you translate them, they would land right on top of each other and be congruent. So something like that and that would be corresponding. So if I'm looking at my picture here, I've got these two parallel lines cut by that transversal. It looks to me like that angle right there is corresponding with that angle right there. So if you're trying to visualize this in your head, it's like if I slid that angle over here, they would match up perfectly. So I can't say angle B and angle C just because C's got too many things going on. So I'm going to say angle ABC congruent to angle DCE. Remember, the vertex of your angle needs to go in the middle for the letterings there. So if I mark that, that actually looks like enough information. I've got side, angle, side here because I had a lot of information in the givens. So I can say that triangle ABC is congruent to triangle DCE just by side, angle, side there. So sometimes when we're given parallel lines, we'll be looking for alternate interior angles. Other times, like this one, we'll be looking for corresponding angles. Number 18. Given segment AE bisects segment BD and segment AB parallel to segment DE, prove those two triangles are congruent. So as always with all of my proofs, I'm going to start off with my givens. They tell me that AE bisects BD and that my other two segments AB and DE are parallel. The reason I know that's true is because they're given. So I'm going to start with my bisecting part. If BD is getting bisected, then it should be the case that it's cut into two congruent segments, BC and DC. And I'm just going to write the definition of a segment bisector. A segment bisector divides a segment into two congruent segments. So that's my reason there. So I took care of the first part of the givens. Now I need to ask myself, why did they tell me that my two segments are parallel? And if I'm looking at my parallel lines, cut by that transversal right there, it looks like I've got some congruent alternate interior angles at B and D. So I'm going to start by saying angle B is congruent to angle D. Reason being, parallel lines form congruent alternate interior angles. Now that's if I look at transversal BD. If I instead decide to look at AB, go down transversal AE and go back up, I've got another pair of alternate interior angles at A and E. So I can include that in my proof as well for the same reason, so I don't need to make it another step. So, again, I've got two angles and the side that's not in between them. So these two triangles are again congruent. Triangle ABC congruent to triangle DCE by angle, angle, side. Now it's worth noting here, this actually could have been an angle, side, angle proof as well if you decided to use these vertical angles in your proof as well, in case you didn't want to use both pairs of alternate interior angles, and you're more than welcome to do that. So for a lot of these proofs, there'll be more than one correct way to do them. Number 19. Given segment PS congruent to segment QR and segment PQ congruent to segment SR, prove that PQ is parallel to segment SR. And again, if you're trying to prove that lines are parallel, it's a good idea to look for alternate interior angles that you could hopefully prove congruent. So if I can get to a point where I could say that those two angles are congruent, I'd be able to say that the lines are parallel. But the first thing I'm going to do is I'm going to try to think about a triangle proof. Statements, reasons. All right, let's pretend I wrote my givens down there, and I'm going to think a little bit. Well, the only thing I really notice in my picture is that these two triangles share PR. So I'm going to say that segment PR is congruent to segment PR by the reflexive property. Now, they gave me a lot of information in the givens here. So this is enough to say that these two triangles are congruent. Triangle PQR and triangle RSP, because all the sides are the same. So I can use a side-side-side argument. Now here's where we need to think a little bit. Remember, the goal here was to be able to say that these angles were congruent, so that I could say, hey, my lines have to be parallel because the alternate interior angles are congruent. So let's think about that. I've proven the triangles are congruent, and I'm trying to make an argument that angle QPR, the top one, is congruent to angle PRS. So remember, if my two triangles are congruent, the reason why any corresponding segments or angles would be congruent would be that corresponding parts of congruent triangles are congruent. CPCTC. So I can't say anything about congruent alternate interior angles here because I don't know that the lines are parallel yet. My whole goal of this is to prove that the lines are parallel. So I can't make any assumptions based off of the lines being parallel. So now that I have those alternate interior angles, I can say that congruent alternate interior angles form parallel lines. So because the alternate interior angles are congruent, it must be the case that segment PRQ is parallel to segment PR. Number 20. In the diagram of triangle LAC and triangle DNC below, they're telling me that LA is congruent to DN, CA is congruent to CN, and DAC, so that segment right there, is perpendicular to LCN. Remember, the perpendicular lines, when they intersect, they form congruent right angles. And they want me to prove that these two triangles are congruent. Again, just for sake of time in the video, you still need to write your givens. I'm going to skip that step just so we can analyze it a little bit. So really the only piece of information that they didn't explicitly tell me were that those two were congruent right angles. So if I wanted to, I could say angle ACL congruent to angle NCD, those two right angles. Or if you weren't sure how to name those, a quick trick is that you could always label them as angle 1 and angle 2 to make them a little bit easier to reference, so that to say that angle 1 is congruent to angle 2, reason being perpendicular lines form congruent right angles. Now, why would these two triangles be congruent? Do we have enough information here? Well, it's kind of hard to see because of the way that they're oriented. But if I redraw DNC so that it's oriented the same way as my other triangle, right? I've got my right angle C right here and over here in D. I know that CN matches up with CA. I know that I've got the right angle right there, and I've got a DN right there. So this could be a side-side angle argument, but you got to remember, side-side angle isn't going to work unless it's a right triangle, which it is. So we can make a hypotenuse leg argument. Triangle LAC is congruent to triangle DNC by hypotenuse leg. Now it wants me to describe a sequence of rigid motions that would map triangle LAC onto triangle DNC. So if I'm starting here, it looks like if I just spin it around a little bit, because I know A needs to land on N, C is not going to move, but L should map to D, I'd be done. So I'm going to say rotate. I need to state a center of rotation and how much. So I'm going to say rotate about point C, and you have to pick a direction as well. Remember, that direction is going to be counterclockwise. Counterclockwise 90 degrees. Now you could say 90 degrees because we know for sure that these are right angles. If you weren't sure what the angle measurement is, you could say rotate until point L maps to point D and until point A maps to point N, because that would also be a specific rotation to tell me how far to go. Number 21. Given DB is the perpendicular bisector of AC, prove that we have an isosceles triangle there. So this one's going to be a little bit more intensive, because remember that isosceles triangles has two congruent sides and two congruent angles. So if we could show either of these things to be true, we don't need to show both, just one of them, that would be enough to prove that my full triangle ADC is isosceles. Now, I don't really know where to start, but a triangle proof is always a good idea to start with if you don't know where to go. Because if I was able to prove these two triangles are congruent on either side, I could say that those sides AD and DC were the same by CP/CTC, and that would be enough to show that the triangle is isosceles. So let's get going somewhere. Again, just because it takes me a while to write it, I'm going to skip writing my givens for now, but you do need to write them. It tells me that DB is the perpendicular bisector. That's two pieces, right? The perpendicular part means that it's going to intersect my other side, making right angles. So I'm going to label that as just angle 1 and angle 2. And the bisector part, it's not bisecting that angle up there. Read carefully. It's saying it's the bisector of segment AC. So it's bisecting the segment below down here, saying that AB and BC are the same. So I'm going to start with angle 1, congruent to angle 2. And I know that because of the perpendicular part, right? Perpendicular lines form congruent right angles. And again, feel free to use the perpendicular symbol if you don't want to write out the whole word. And I also know from the bisector part that segment AB is congruent to segment BC, because the segment bisector divides a segment into two congruent segments. Well, in order to prove two triangles are congruent, I need three congruent pieces. Right now I only have two. But I notice that they share a side. So it's not in my givens, but I can still say it's true because I see they share DB. So that's going to be a reflexive property. So I'm going to say that my left triangle, ABD, is congruent to triangle CBD by side angle side. And now remember the goal here. This isn't a triangle proof. It's a proof to say that my big triangle ADC is isosceles. And we've got two options at this point. You can make an argument to say that angle A and angle C are the same by CP/CTC, and you have enough to say it's isosceles. But instead, I'm going to go the side route. And I'm going to say that those two sides, AD and DC, are definitely congruent by CP/CTC. Because if the two triangles on the outside are congruent, then it must be the case that all the corresponding pieces are also congruent. And if I have those two congruent sides, that's enough for me to say the triangle ADC is isosceles. Reason being that isosceles triangles have two congruent sides. And again, if you went the angle route here and step 6 instead said angle A congruent to angle C, you would just have to say that isosceles triangles have two congruent angles instead, because that's the argument you formed.